In this video, we will explore some visualizations of the integration rules, of the approximate integration rules that we just discussed, namely of the midpoint, trapezoidal, and the Simpson rule. And what you're looking at is a notebook called a Jupyter notebook. So you may be familiar with Jupyter notebooks for Python. This is a Jupyter notebook for SageMath. So SageMath is an open source free software for mathematical computation. And you can get a copy from sagemath.org. It runs on every major platform, Linux, Windows, and Mac. You can go to sagemath.org and download your copy and get the source code of this notebook that I'm looking at from the course webpage, and then run it on your own computer. So what we'll do here is we will, so what this notebook does is it introduces the necessary definitions for these approximate integration rules. So specifically, these here are the definitions of the coefficients in three integration rules. So if you recall, in our integration rules, we had these coefficients. So for example, these are the coefficients for the Simpson's rule. And then before that, we had coefficients for trapezoidal rule of the form 1, 2, 2, 2, 1. And finally, for the midpoint, coefficients were the simplest. They were just all ones. So that's what this cell does, more or less. Then in the next cell, we actually run these approximations, run these approximate rules, and we tell Sage to manipulate, to run this routine in an interactive way, so that we can adjust the function that is being integrated, the number of subintervals, and the method that is being used. What this output tells us is it computes the value of the corresponding rule, so say trapezoidal rule in this case, since we have chosen trapezoidal rule, for cosine x from -1 to 1. Okay, so it computes the nth partial sum for the trapezoidal rule. So you can see that it contains 13 terms because it's the trapezoidal rule, so you have n plus 1 terms. So here's the value obtained by evaluating the nth trapezoidal sum, and it approximates the precise value of this integral, which is given here. And so then we analyze errors that these integration methods give. And so the errors are are computed by taking the difference between the precise value of the integral and the output of this summation here. And so what we are comparing here is we have our implementation of the trapezoidal rule, which is done using the formulas from the course over here that you have seen. And so this error is compared with the built-in default method. So quad stands for quadrature. That's the default built-in method for computing quadratures or definite integrals in SciPy. It also so this also compares our output with the error of the built-in trapezoidal method in SciPy and the built-in Simpson's rule in SciPy. So as you can see, the error of our naive implementation for n equals 12 is actually smaller than the built-in trapezoidal rule. So it actually performs better than the built-in trapezoidal rule. So these vertical lines denote the xi's, the endpoints of subintervals in partition of -1, 1. So let's look at what happens when we change the method from trapezoidal rule to midpoint rule. So note the error for trapezoidal rule. So we have 0.0038. Let's switch to the midpoint rule. And so you can see that the error for midpoint rule is about 2 times smaller than that for the trapezoidal rule. So exactly as we discussed previously, we have this relation between the magnitudes of errors of trapezoidal and midpoint rule, and midpoint rule is about 2 times better. It has about 2 times smaller error for the same number of subintervals. And so, yeah, so in this case, midpoint clearly beats the built-in trapezoidal rule, and even beats the built-in Simpson's rule, which is rather surprising. But of course, it's much, much worse than the built-in quadrature method, which uses some more advanced techniques, and it achieves an error of 10 to the minus 14, which is pretty close to the machine precision. So let's see what happens as we increase the number of subintervals in the partition to the maximal which this slider will allow, and that is 30 subintervals. And so you can see that it's actually the error for the midpoint rule is much smaller now than it used to be. It's still very far away from the built-in quadrature method. And so I just actually noticed that there was a bug in how we computed the built-in methods. So I just fixed that. So now we can see that indeed the error of the midpoint rule goes down significantly when we increase the number of subintervals to 30, but so does the error for the built-in trapezoidal rule. And I think I still have, oh no, this is right. So this is the Simpson's rule. So Simpson's rule at this point is slightly better, well, as expected. Actually, not slightly, but significantly better than the built-in trapezoidal rule or our trapezoidal rule. But it's rather curious that our trapezoidal rule is actually outperforming the built-in method for trapezoidal rule. So that's quite interesting. So again, let's switch to midpoint rule. Yeah, so that's quite an improvement of what we had for 10 subintervals, but still very far away from the default method for definite integrals in SciPy. Right, so as you can see, the errors for trapezoidal and midpoint rule are indeed related with this ratio of 2. So trapezoidal rule is about 2 times larger than the midpoint rule, and it has the opposite sign. So the midpoint rule in this case has negative sign, trapezoidal rule has positive sign. And finally, let's just look at how this compares to our implementation of Simpson's rule. So you can see that this is about this is 30 times 10 to the minus fifth, whereas error of the built-in Simpson's rule is 1 times 10 to the negative fifth. Let's check out our own implementation of Simpson's rule, and hooray, it actually beats the built-in Simpson's rule. I'm rather surprised by this. So it basically means that the implementation of Simpson's rule that we have here is surprisingly better than what SciPy has built in. So that's rather encouraging, I would say. But you can see that this is much, much better than the midpoint rule. So once again, this is 1 times 10 to the minus 7th, whereas with midpoint rule, we used to get 3 times 10 to the negative 4th. Right, so this is 3 orders of magnitude. It's 1,000 times, more or less 1,000 times more precise method in this setting. With the same number of subintervals in our partition, we're getting much, much more precise estimate. So I should maybe say a couple of words about this picture. So you can see that some of the vertical lines are lighter, and so this corresponds to the triples of points that give that result in a single parabola. So if you take 2 adjacent intervals in the partition, Simpson's rule will draw a parabola through the 3 points on the graph that correspond to their endpoints. So that is why Simpson's rule is so much more precise. It uses higher order approximation, the approximation with parabolas in place of approximation with straight lines, as do the midpoint and the trapezoidal rule. But of course, you can see that this computer algebra system, the SageMath, uses some even more advanced methods that allow to get much, much better precision here. So instead of 1 times 10 to the negative 7th, it allows to get precision of 1 times 10 to the negative 14th. And so the limitation of improving precision even further after this error would be the machine precision. So the standard double precision means that you store a single floating point number in 64 bits of memory. And so that allows you to store about numbers down to about 10 to the minus 16th. And so basically making this computation even more precise means that you need to use more than 64 bits per floating point number to attain that precision. So that requires some specialized tools, but I should say that SageMath does have built-in high precision libraries that will allow you to do that should you need to compute integrals to very high precision. Yeah, so if you do download this notebook, you can change the function that is being integrated to pretty much any function, and look at compare the different precisions, the different errors for different functions that these methods can give you. So for example, we just tried sine of x, here is cosine of x. So you see that the built-in method consistently gives the error of 10 to the negative 14. Pretty much no matter which function I put in, assuming it's a nice function. Another rather curious observation is that when we integrate an odd function such as tangent or sine, there's apparently some cancellation of error, and we get much, much better results even with our naive implementation of the Simpson's rule. So let's try midpoint rule for the sake of comparing it. So apparently midpoint rule gives exactly the 0 value, which is of course the value of the integral here. We're integrating an odd function on a symmetric interval, so we must get 0, and so in this case, incidentally, we do get 0 using midpoint rule, so we get perfectly precise answer. So yeah, so if you want to play with it, with this notebook further, you can download your own copy of SageMath and then load this notebook into the system. And there are some further comments about how the coefficients here are determined from the formulas for approximate integration rules. And there is some additional code that concerns Euler's method. So Euler's method is an approximate method for solving differential equations, and that is something that we want to discuss next.